Welcome! In this session, we will be diving into LeetCode problem number 1606, find servers that handled most number of requests. This problem challenges us to determine which servers handled the maximum number of requests efficiently while adhering to specific constraints. Let's explore the problem and break it down step by step. In this problem, you are given a set of K servers numbered from 0 to K1 that process incoming requests. These requests arrive at specific times, which are provided in the arrival array. Each element arrival, I, represents the time, in seconds, when the ith request arrives. Additionally, the load array specifies the processing time for each request, where load, I, indicates how long the ith request will occupy a server. Importantly, each server can only handle one request at a time. If a request arrives and all servers are busy, it is dropped. However, if one or more servers are free, the request is assigned to the lowest numbered available server. At the end of the process, you need to identify which server, or servers, handled the most requests. If there are ties, the indices of the servers should be returned in ascending order. The output of this problem is a list of integers representing the indices of the servers that handled the maximum number of requests. Let's consider an example to understand this. Suppose K equals 3, arrival equals 1, 2, 3, 4, 5, and load equals 5, 2, 3, 3, 3. For the first request, which arrives at time 1, server 0 is free, so the request is assigned to server 0, and it remains busy from time 1 to 5. The second request arrives at time 2, and server 1 is free, so it is assigned to server 1, which will be busy from time 2 to 3. This process continues based on which servers are free when each request arrives. For the third request, which arrives at time 3, server 2 is free and processes the request until time 5. When the fourth request arrives at time 4, all servers are busy, so the request is dropped. Finally, the fifth request arrives at time 5, and server 1 becomes available again. Server 1 processes the request from time 5 to 7. After processing all requests, server 1 handled the most requests, with a total of 2, so the output is 1. Now consider another example, where K equals 3, arrival equals 1, 2, 3, 4, and load equals 1, 2, 1, 2. This time, server 0 processes the first request, server 1 processes the second, and server 2 processes the third. The fourth request is assigned back to server 0, which processes it from time 4 to 5. In this case, server 0 ends up handling the most requests, with a total of 2, so the output is 0. Let's review one more example where K equals 3, arrival equals 1, 2, 3, and load equals 10, 12, 11. Here, the first request is assigned to server 0, which processes it from time 1 to 10. The second and third requests arrive while server 0 is still busy, so both are dropped. As a result, server 0 handled the most requests, with just 1, and the output is 0. The problem comes with a few constraints and edge cases to consider. First, the number of servers K and the number of requests N can each go up to 100,000, making efficiency critical. All arrival times are strictly increasing, and both the arrival times and load times can be very large, up to 10 to the power of 6 and 10 to the power of 5, respectively. Some edge cases include situations where all requests are dropped, such as when one server is perpetually busy, or when there is only one server handling all requests. Another interesting case is when multiple servers process the same maximum number of requests, in which case their indices must be returned in sorted order. Understanding these constraints and edge cases is key to implementing an efficient solution for this problem. To solve the problem of finding servers that handled the most requests, we first considered a brute force approach. The intuition behind this method is straightforward. For every incoming request, we iterate through all servers in a circular manner, starting from the server index determined by I%K, where I is the request index and K is the total number of servers. For each server, we check if it is available by comparing its processing completion time with the current request's arrival time. If the server is free, we assign the request to it and move on to the next request. Throughout the process, we maintain a count of how many requests each server processes. While simple to understand, this approach has a time complexity of O(n*k), which can become highly inefficient when both the number of requests and servers grow large. The space complexity is O(k), as we only need to store the request counts for each server. Although the brute force approach provides an intuitive starting point, it does not scale well for larger inputs due to the repeated checks for server availability. To address this, we consider an optimized approach that uses more efficient data structures. The key idea is to manage server availability and assignments more systematically using a combination of a priority queue and a balanced set or cyclic list. The priority queue, implemented as a min heap, tracks busy servers by storing their completion times and IDs, enabling efficient updates as servers finish processing. Meanwhile, the balanced set of available servers allows us to quickly locate the next server starting from %k in a cyclic manner. The steps include iterating through the requests, moving completed servers from the busy queue back to the available pool, and using modular arithmetic to determine the starting index for assigning the current request. The selected server is then removed from the available pool, added to the busy queue with its updated end time, and its request count is increment. At the end of the process, we identify the servers with the highest request counts. The optimized approach significantly improves efficiency, with a time complexity of n*log k. This improvement comes from the logarithmic time required for heap operations, as opposed to the linear scans in the brute force method. The space complexity remains k, accounting for the storage of the heap and the server counts. Several key insights make this solution both efficient and fair. First, the use of modular arithmetic ensures that server selection is cyclic, distributing the workload evenly and fairly. Second, the priority queue minimizes the overhead of managing busy servers by allowing us to quickly retrieve and update servers as they become free. Lastly, balancing the workload across servers ensures that all constraints of the problem are met while maximizing efficiency. The optimized approach was chosen because it strikes an excellent balance between efficiency and scalability. While the brute force method is simpler to implement, it cannot handle larger inputs due to its prohibitive runtime complexity. By leveraging the priority queue and cyclic set, the optimized strategy achieves a significant reduction in runtime without sacrificing correctness or fairness. However, this approach does introduce some trade-offs. Specifically, the use of additional data structures makes the implementation slightly more complex. Despite this, the benefits far outweigh the downsides, as the optimized solution is well suited for large-scale input scenarios. By ensuring fairness in server selection through modular arithmetic and efficiently managing server availability with a heap, this approach meets all problem constraints effectively. This combination of correctness, fairness, and scalability makes it the ideal solution for this problem. In this problem, we are tasked with determining which servers handle the most requests under specific constraints. Servers are indexed from 0 to K1 and process requests sequentially, one at a time. If a server is busy at the time a request arrives, that request is dropped. To solve this, we start by initializing the necessary data structures. First, we parse the input, the number of servers K, the arrival times of requests, and their corresponding load times. We create an array requests_handled of size K to track the number of requests each server processes, starting with all zeros. To efficiently manage server availability, we use a priority queue, or min heap, to track busy servers. Each heap entry contains the n_time of a server's current task and its server_ID, allowing us to quickly identify servers that finish first. Additionally, a set of free server indices enables efficient allocation when assigning requests. This setup ensures we can manage server states dynamically as requests arrive sequentially. To process requests, we iterate through each request in the arrival array. At each step, we first check the priority queue to update the status of busy servers. If a server's n_time is less than or equal to the current arrival time, it is removed from the heap and added back to the free servers set. Next, we determine which server will handle the current request. If the free servers set is empty, the request is dropped. Otherwise, we calculate the preferred server index using %k, where I is the request's index. Starting from this preferred index, we iterate over the free servers in increasing order, wrapping around to 0 if necessary, and select the first available server. Once a server is chosen, we update the data structures, the request is assigned to the server, its count in requests_handled is increment, and it is removed from the free servers set. The server's new end underscore time, calculated as arrival, I, plus load, I, is pushed to the priority queue. This ensures that our algorithm dynamically allocates requests while respecting server availability. A few key insights help us understand why this approach works efficiently. First, the use of I%K ensures a fair distribution of requests by starting the search for a server at the preferred index, balancing load across all servers. The circular wraparound ensures that we always stay within valid server indices when iterating through the free servers set. The priority queue plays a critical role in efficiently managing busy servers, allowing us to retrieve and update the next available server in logarithmic time. Meanwhile, the free servers set enables quick decisions about which server can handle a request. For edge cases, our algorithm gracefully handles scenarios like all servers being busy, or requests are simply dropped. Together, these insights combine to create an efficient and scalable solution. The choice of data structures, priority queue, set, and array ensures that we maintain optimal performance while effectively managing server states and load distribution. Now, let's analyze the algorithm's complexity. For n requests and k servers, the most computationally expensive operation is updating the heap, which takes O log k time per request. In the worst case, iterating over the free servers set may take O k time. Combining these operations, the total time complexity becomes O n asterisk log k plus k. For space complexity, we require O k plus n due to the heap, the free servers set, and the input data. To solidify our understanding, consider an example where k equals 3, arrival times are 1, 2, 3, 4, 5, and load times are 5, 2, 3, 6, 8. This example will illustrate how requests are sequentially assigned to servers while managing their availability dynamically. Let's walk through the example step by step. The first request arrives at time 1, and server 0 is the preferred server since 1% 3 equals 0. Server 0 is free, so it handles the request, and we update the busy heap with 6, 0, where 6 is the end time. The second request arrives at time 2, and server 1 is preferred. Since it's free, it handles the request, and we add 4, 1 to the busy heap. The third request arrives at time 3, with server 2 as the preferred choice. Server 2 handles the request, and 6, 2 is added to the heap. This process continues for subsequent requests, ensuring that each is either assigned to an available server or dropped if no server is free. At the end, we identify the maximum value in requests underscore handled and return the indices of servers that processed the most requests. This completes the algorithm, providing an efficient and robust solution. Here, we begin our Python implementation by importing the necessary libraries, Heap for managing our priority queue and defaultdict for handling dictionaries with default values. We define a class solution and within it, the method busiestServers. The method takes 3 parameters, k, the number of servers, arrival, a list of arrival times for requests, and load, a list of processing times for those requests. We initialize a set available underscore servers containing all server indices, as they are initially free. A min-heap, busy underscore servers, is used to track servers currently processing requests, storing tuples of end underscore time, server underscore ID. Another list, request underscore count, keeps track of how many requests each server has handled, initialized to 0 for all servers. Next, we iterate over each request using a loop. For each request, the first step is to free up any servers whose processing has completed by the current start underscore time. This is done by checking the busy underscore servers heap and reinserting those servers back into the available underscore servers set. If free servers are available, we determine which one should handle the request. We calculate mod underscore index as I%K, which helps us start searching from a specific server index, ensuring a round-robin allocation. Servers in available underscore servers are sorted to prioritize those with indices closest to mod underscore index. The first server in this sorted list is selected, removed from available underscore servers, and added to busy underscore servers with its new end time. We also increment the request underscore count for this server. Finally, to determine the busiest servers, we find the maximum value in request underscore count and return a list of all server indices that handled this maximum number of requests. Here, we start by defining the busiest servers method, which takes three inputs: the number of servers k, the arrival times of requests, and their respective processing times in the load array. We initialize a tree set called available servers to keep track of all currently free servers, starting with all k servers marked as available. We also use a priority queue named busy servers to manage servers that are currently processing requests. This queue is sorted by the end times of the requests being processed, ensuring that the earliest free servers are prioritized. Additionally, we maintain an array request count to track how many requests each server has handled. Next, we iterate through the arrival array, processing each request one by one. For each request, we first check the busy servers queue and free up any servers that have completed their processing by the current arrival time. This is done using a while loop that removes servers from busy servers and adds them back to available servers. Then, we attempt to assign the current request to one of the free servers. To do this, we use the ceiling method of treeset to find the next available server with an ID greater than or equal to the current request's index modulo k. If no such server exists, we wrap around and select the first available server. Once we identify the server, we remove it from the available servers set and assign the current request to it. We calculate the server's new busy period by adding the request's load time to its start time and then add this information to the busy server's queue. We also increment the request count for the selected server in the request count array to keep track of how many requests it has handled. After processing all requests, we determine the maximum number of requests handled by any server using the max method from the array's utility class. We then iterate over the request count array to find all servers that handled this maximum number of requests and add their IDs to the result list. Finally, we return the result list, which contains the IDs of the busiest servers. This implementation ensures that we efficiently manage server availability in busy periods while keeping track of request counts, making it well suited for handling large datasets. Here, we begin with an example where we have 3 servers and 5 requests arriving at times 1 through 5. Each request has a specific processing time provided in the load array. Initially, all servers are free, so the available_servers set contains servers 0, 1, and 2. The busy_servers heap is empty since no servers are handling requests yet. Also, we initialize request_count to keep track of the number of requests handled by each server. For the first request arriving at time 1, the algorithm checks the busy_servers heap but finds no servers to free since it's empty. It then starts searching for an available server starting from index i%k, which is 0. Server 0 is selected, assigned the request, and is marked as busy until time 6. The available_servers set is updated to exclude server 0. The busy_servers heap now records that server 0 will be busy until time 6, and request_count reflects that server 0 has handled 1 request so far. In this step, the second request arrives at time 2. Again, no servers are freed since the current time is less than the next available time in the busy_servers heap. The algorithm starts searching for an available server from index i%k, which is 1. Server 1 is free and gets selected for this request. Server 1 is then marked as busy until time 4. The available_servers set is updated to remove server 1, and the busy_servers heap reflects that server 1 will be busy until time 4. Similarly, request_count is updated to show that servers 0 and 1 have each handled 1 request. Next, request 2 arrives at time 3. Again, no servers are freed because the current time is still less than the next available time. The search begins from index i%k equals 2, and server 2 is available and selected. Server 2 is marked as busy until time 6, and the busy_servers heap is updated accordingly. At this point, all servers are busy, and request_count shows each server has handled 1 request so far. Now, request 3 arrives at time 4. The algorithm first frees any servers whose busy time has ended. Server 1, which was busy until time 4, is freed and added back to the available_servers set. The search for an available server starts from index i%k equals 0. Since server 1 is now available, it is selected for this request. Server 1 is marked as busy again, this time until time 7. The busy_servers heap is updated to reflect its new busy time. The available_servers set becomes empty once more, and request_count now shows that server 1 has handled 2 requests, while servers 0 and 2 have each handled 1. For request 4, which arrives at time 5, no servers are freed since all currently busy servers are still occupied. The search begins from index %k equals 1, but because no servers are available, this request is dropped. Finally, the algorithm identifies that the maximum number of requests handled by any server is 2, and server 1 is the only server that handled the most requests. The output for this example is 1. Here, the output of example 1 is summarized as 1, indicating that server 1 handled the most requests. We then move on to another example where all requests are dropped. In this case, we have 2 servers and 4 requests arriving at times 1 through 4, each with a processing time of 10. At the start, both servers are free, so the available_servers set contains servers 0 and 1, and the busy_servers heap is empty. The request_count array is initialized to 0 for both servers. For the first request, which arrives at time 1, the algorithm checks the busy_servers heap but finds no servers to free since it's empty. Starting the search from index %k equals 0, server 0 is available and selected for this request. Server 0 is marked as busy until time 11, and the busy_servers heap is updated to reflect this. The available_servers set is updated to exclude server 0, and request_count shows that server 0 has handled 1 request. When the second request arrives at time 2, no servers are freed since the current time is less than the next available time in the busy_servers heap. The search begins from index %k equals 1, and server 1 is available and selected. Server 1 is marked as busy until time 12, and the busy_servers heap now tracks both servers' busy times. The available_servers set becomes empty, and request_count shows that both servers have each handled 1 request. When the third request arrives at time 3, the algorithm checks for any free servers but finds none, as both servers are still busy. It starts searching from index %k equals 0, but no available servers are found, so this request is dropped. Similarly, for the fourth request arriving at time 4, no servers are freed, and no available servers are found starting from index %k equals 1, so this request is also dropped. At the end of this process, no server handles more than 1 request. The maximum number of requests handled is 1, and both servers 0 and 1 share this maximum count. The output for this example is 0, 1. In this example, we examine a scenario with uneven load distribution. We have 2 servers and 4 requests arriving at times 1, 3, 5, and 7, with varying processing times of 4, 1, 4, and 1 respectively. Initially, both servers are free, so the available_servers set contains servers 0 and 1, and the busy_servers heap is empty. The request_count array is initialized to 0 for both servers. For the first request, which arrives at time 1, server 0 is available and selected. Server 0 is marked as busy until time 5, the available_servers set is updated to exclude server 0, and the busy_servers heap records that server 0 will be busy until time 5. The request_count array shows that server 0 has handled 1 request. Next, for the second request arriving at time 3, server 1 is available and selected. Server 1 is marked as busy until time 4, and the available_servers set becomes empty. The busy_servers heap is updated to track both servers' busy times, and request_count now shows that both servers have each handled 1 request. When the third request arrives at time 5, server 1 has become free and is selected for this request. Server 1 is marked as busy again until time 9, and the busy_servers heap reflects its new busy time. The available_servers set is updated to include server 0, and request_count indicates that server 1 has now handled 2 requests. Finally, for the fourth request arriving at time 7, server 0 is freed and selected. Server 0 is marked as busy until time 7, and the busy_servers heap is updated accordingly. Both servers have now handled 2 requests each. At the end of this example, the maximum number of requests handled by any server is 2, and both servers 0 and 1 share this maximum count. The output for this example is 0, 1, indicating that both servers handled the most requests. To analyze the time complexity of our solution, we start by breaking it into smaller components. First, during initialization, we create the available_servers set and the request_count array, both of size k, which takes k time. Additionally, the busy_servers heap is initialized as empty, which is an O1 operation. Next, we move to the main loop where we process the n requests from the arrival array. For each request, we may need to free up busy servers. Since each server is added to and removed from the heap exactly once, and both operations take log k, the total cost for freeing servers across all requests is log k. Furthermore, when finding the next available server, we use the sorted function on the available_servers set, which can involve sorting up to k servers. In the worst case, where this sorting happens for every request, it adds k*log k to the complexity. Finally, updating heaps and counters involves operations like removing a server from available_servers, adding it to busy_servers, and incrementing the request_count. These contribute n*log k. Breaking down the remaining steps, once all requests are processed, we need to find the servers that handled the maximum number of requests. First, calculating the maximum value in the request_count array takes k. Then, iterating through the request_count array to identify all indices matching this maximum value also takes k. Together, these steps contribute k to the overall complexity. Combining all components, the dominant term in our time complexity is n*k*log k, which arises from the sorting step within the main loop. Therefore, the overall time complexity of the solution is n*k*log k. This includes all initialization, processing of requests, and determining the servers with the maximum requests. Now let's examine the space complexity. The solution requires several data structures to manage the server states and requests. The available_servers set can hold up to k servers, contributing k space. Similarly, the busy_servers heap, which tracks servers currently handling requests, also requires k space. The request_count array, used to store the number of requests handled by each server, is another k structure. Beyond these, there are temporary variables like sorted_servers, which holds a sorted version of available_servers during each request. Since this temporary array can also contain up to k elements, it adds another k to the space complexity. Altogether, the total space complexity is dominated by these data structures, resulting in k. To appreciate the efficiency of the current approach, we can compare it to a naive solution. A straightforward approach might involve iterating through all k servers for each of the n requests to check for availability. This would lead to a time complexity of n*k, as it does not use efficient data structures. Additionally, managing busy servers without a heap would require more manual checks, further increasing the time complexity. In contrast, the current solution optimizes server management by using a heap for efficiently handling busy servers, with log k operations for additions and removals. It also uses modular arithmetic and sorting to identify the next available server. While the sorting operation adds complexity, specifically k*log k per request, it ensures we avoid brute force checks and maintain correctness. This trade-off allows the solution to efficiently handle large inputs while keeping unnecessary computations to a minimum. Finally, let's consider the best, worst, and average case scenarios. In the best case, most servers remain idle, and there is minimal overlap between requests. Here, the sorting step is rarely needed, and freeing up servers from the heap is minimal, bringing the time complexity closer to n*log k. In the worst case, all servers are busy, and each request requires sorting the entire available_servers set, resulting in the highest complexity of n*k*log k. For average cases, where some servers are busy but not all, the performance typically lies between the best and worst cases, leaning toward n*k*log k. Overall, the solution successfully balances the trade-off between time and space complexity, leveraging efficient data structures like heaps and sorting to ensure correctness and scalability, even for large-scale inputs. Although the worst-case complexity is high, the optimized approach is a significant improvement over naive alternatives. When tackling this problem, there are some common mistakes to watch out for. First, not handling server availability correctly can be a major pitfall. Each server can only process one request at a time, so assuming that a server can handle multiple requests simultaneously violates the problem's constraints. Ensure that servers are released only after their assigned processing time has elapsed. Next, inefficiently iterating through all servers to find the next available one is another frequent issue. A linear search for each request can become too slow when dealing with large inputs, as it results in an O(k*(n) time complexity. Using a balanced data structure, like a heap, allows for efficient server management and drastically improves performance. Finally, ignoring modular arithmetic when assigning servers is another critical mistake. Server indices should wrap around cyclically, meaning when you reach the last server, you need to loop back to the first. Failing to implement this properly can lead to invalid indexing or skipped servers, resulting in incorrect assignments. Another common mistake is not sorting requests by their arrival time. Processing requests in the given order without ensuring they are sorted can lead to logical errors, especially when handling overlapping requests or managing server availability. Always check that the requests are ordered correctly before processing. Additionally, mismanaging overlapping requests is a frequent challenge. If servers are not released on time when a new request arrives, they might remain locked unnecessarily, even when they should be available. Overlapping requests require careful management of server release times, and a min-heap is an effective tool to ensure servers are freed in the correct order based on their finish times. Now, let's focus on some key insights that can help during interviews. A deep understanding of the core data structures is essential. For example, heaps, or priority queues, are critical for managing servers efficiently, and modular arithmetic is fundamental for cyclic server assignment. It's also important to discuss optimal trade-offs. While a naive O(k*(n) solution might work for small inputs, it's not scalable for larger datasets. Optimizing to O(n*(log)k) using a heap makes the solution much more efficient. Additionally, this problem mirrors real-world load balancing in distributed systems, so drawing an analogy to these scenarios can demonstrate a broader understanding of the topic. Be prepared to handle edge cases as well, such as when there are more requests than servers, simultaneous arrivals of multiple requests, or when servers remain idle for long periods. Addressing these edge cases effectively shows a comprehensive grasp of the problem. This problem shares similarities with other well-known LeetCode challenges, which makes it helpful to explore related problems. For instance, LeetCode 621, Task Scheduler, also involves scheduling tasks while accounting for idle times. Similarly, in LeetCode 1834, Single-Threaded CPU, you focus on scheduling tasks based on their availability and processing requirements. Another closely related problem is LeetCode 253, Meeting Rooms 2, which uses heaps to determine the minimum number of meeting rooms needed. Finally, LeetCode 857, Minimum Cost to Hire K-Workers, incorporates heap-based optimization techniques to solve a cost-efficiency problem. Reviewing these problems can help reinforce your understanding of similar patterns and techniques. When considering alternative approaches, it's important to evaluate the trade-offs of each. The brute force approach checks server availability linearly for each request. While simple to implement, it has a time complexity of O(k*(n), making it inefficient for larger datasets. A more scalable solution is the heap-based approach, which uses a min-heap to track server availability based on finish times. This reduces complexity to O(n*(log)k) and is better suited for handling larger inputs, though it requires a deeper understanding of heaps. Another option is to use modular arithmetic with binary search. By pre-computing server indices and leveraging binary search for faster assignment, you can achieve a similar complexity of O(n*(log)k). While this method may use additional space for pre-computed indices, it simplifies the logic for assigning servers cyclically, making it another viable alternative for efficient implementation. Thank you for joining me on this walkthrough of LeetCode problem number 1606, Find servers that handled most number of requests. We summarized the use of priority queues and modular arithmetic to solve this problem efficiently. Remember, practicing such problems will strengthen your problem-solving skills for both coding interviews and real-world challenges. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!